Okay. Hi, everyone. We're going to start the afternoon session. I hope you found the posters in the other building, West building. We had like so many people coming over here. So we are going to kick off the afternoon with Angela Dai, assistant professor in Munich. Not going to give a big introduction, but congratulating here officially on her starting grant. That's huge in Europe. And yeah, very much looking forward to your talk, Angela. Thanks.
Thanks, and thanks for the introduction and for having me here. I wanted to talk a bit about a slightly philosophical discussion on learning and optimization, in particular for generative models for 3D. So in my lab, we're interested in how we can capture the world in 3D. And in particular from commodity sensor kind of inputs. So for instance, from your iPhone, looking around in these kinds of indoor environments, how can we understand the actual geometric structures underlying these observations, of course, for applications like content creation, creating video game assets that are potentially interactable, that are realistic, or to go for the more traditional computer vision kind of route, how can we get machines to perceive the world similar to how we as humans do and potentially interact with the environment in this way? So there's an interesting interplay here. Keep going, I'm just going to check this. That we've seen in the recent years. So when I started my PhD, we were all pretty much working with optimization in a pretty traditional fashion. So in the context of 3D reconstruction, that would be from an input set of images or RGBD frames. We'd optimize for surface geometry, camera poses from just those observations in one scene. Whereas recently we've seen a lot of work go into how we can learn strong priors, for instance, in this example here on the left, how we can learn about regions that haven't been observed by the set of input images for the 3D reconstruction, information we can only gain through data-driven priors. And now that we're back and seeing the power of things like NeRFs, we've actually come headlong right back into 3D reconstruction as optimization on a single scene basis. So I want to talk a little bit about how we can potentially combine the two of these concepts together. And of course, there are many ways that you can go about it. So just a few examples. So I wanted to go first the route that is probably the most intuitive, which is that we can learn strong priors. For instance, in this case, we want to learn a manifold of plausible shape textures for 3D shapes. If you sample from the manifold, you get a bunch of different textures given an input shape geometry. And what can we use it for? Well, at test time, when given an input image, we can try to map into that manifold and find the code of the shape texture that best represents that input. For instance, in terms of representing the shape texture and appearance of an arbitrary image that's taken from a real world observation. So there are a few challenges here. One is that when we try to learn with supervision, the information we have about textures on 3D shapes is not that great. It's not realistic. For instance, here you see a couple of the ShapeNet objects that have plausible textures, but certainly not anything you would mistake for a real kind of image. Whereas in 2D, we actually have photorealistic images, but of course they're attached only to the image domain rather than 3D. So we'd like to tackle this problem, taking this into account. And so the problem statement here is that we have as input some kind of shape geometry, and we want to be able to learn a manifold that we can then sample textures. And here these textures are attached to the surface geometry of the input shape. So we are inherently learning view consistent formulations in this particular appearance model. And then we want to be able to go from an input query image and transfer the perceptual nature of that image onto a shape geometry without assuming that we actually know any of the geometry of the input image, since in real applications, you probably don't know exactly what the underlying geometry would be or the pose of that particular image. So we want to just be able to transfer the essence of that onto the shape geometry. So we start by learning the texture manifold first. So as input, we are given the shape as a condition. This is being interpreted as a quad mesh, as well as the latent code that should represent the texture. And we have an encoder and decoder that then decodes onto the faces of the input shape. So we learn features on a per face basis that can then be rendered into the 2D domain. And so then you have a very coarse approximation of the texture that only operates on a per face basis. In order to be able to generate high resolutions, we have a local neural field that then interpolates the features on these faces in the barycentric coordinate system that can refine to a high resolution texture on that particular object. So what this looks like in a bit more detail is that because we're operating on a quad mesh, we want to be able to leverage the power of convolutions, that of which is basically being able to apply something akin to a convolution on a neighborhood of mesh faces, which we can do since we can set a fixed max number of neighbors and use that as the convolutional neighborhood, and pooling can be done through a hierarchy in terms of the meshes that you see here that have been pre-processed based on the train shape geometries. So then we can apply just a StyleGAN2 inspired encoder and decoder that operate on the mesh faces of this quad mesh. And so this is pretty much directly borrowing from StyleGAN2, but operating on the quad mesh neighborhood of the faces here. And so this can get you an initial set of face colors, which is what we've done in a previous work of Texturify, but it's limited in terms of the resolution here. So we can only scale up the number of faces so much. And if you look a bit more closely, it's probably more visible on the cars. You can actually see the faces, since this is only on a coarse per face basis. So we can introduce a local neural field to then interpret the per face features and produce the high resolution colors. And since we want to learn this effective high resolution from real world images, we have an adversarial formulation, of which you've seen some other examples already today, that ask whether this is a real image or a fake image from the real image distribution. And this is kind of cool because now we don't have to have any correlation between the geometries that we're using and the images that we're training on, except for the fact that they belong to the same class category. So that actually allows us to learn this nice texture manifold that can produce relatively high resolution and high quality colors on the shapes. And in fact, these are attached to, sorry, PowerPoint, I guess, is not powerful enough to fully render all of these images in sync. But you can see that we can learn these plausible textures on the appearance of the shape. The downside, of course, being that we are learning from real images, and images are not necessarily just shape and materials. There's also a lighting component that ends up baked into the windows of the cars that you can see. But we can still leverage this manifold for this texture transfer from real images. And so we don't want to assume that there's, again, any kind of known shape geometry. So we're looking at the level of patches, and these should be stylistically similar from the rendered result that we're producing and the query image. So that should produce something that's perceptually similar, and in this case captured by a VGG style loss between the patches of the query image and the patches of the textured result that we're trying to optimize for. So for these two examples, you can see the query image on the left and the initial state of the texture shape on the right. And as we go through the optimization process, we get something that becomes more perceptually similar to the query image based on this test time optimization. So that actually lets us move through this texture manifold in order to respect an image as a control for trying to generate textures. So this is just in comparison to a couple of interesting alternative ways to generate textures on 3D shapes. And so here we don't have a query image, but you can see probably the most well-known are EG3D and Get3D that work very well in training conditions where you actually can generate multiple view images. But here we actually have a slightly less constrained setting. We only have one image per real object, for instance, in photo shape for chairs or comp cars for cars. And that means that we can more effectively learn that manifold under this kind of setting. So here you can see now we can get the essence in a sense of some of these query images. These are real world images from ScanNet for the chairs and from comp cars for the cars. And try to transfer over the same kind of characteristics, despite the fact that we might have somewhat different chair or car geometry from the query image, as well as just an arbitrary kind of pose in the view. So I think this is the kind of more classical paradigm where we say we wanted to leverage some kind of strong data-driven prior, and then we can apply test time optimization to walk through that manifold and try to figure out, how we can explain an input. But I wanted to also talk a little bit about the inverse direction, which I think is kind of interesting. Can we leverage the benefit of first trying to do this optimization and then learn the priors, in particular in the context of neural fields? And so that's, I think, particularly interesting for 3D, because if we view the neural fields more as a data structure, right, we can encode a 3D shape, in this case, in a coordinate field MLP. So the XYZ are going to be input into this MLP, and we predict just the occupancy at that particular XYZ location. In this case, occupancy, so it's a binary cross entropy loss. Values outside the surface are then going to be 0. Right, and then we can do this optimization on just one shape, and you can get an extremely high fidelity representation of that shape, encoding in only the few MLP parameters of that neural field. This is also directly applicable for 4D shape sequences. So we can do exactly the same thing for a dynamic sequence. The main difference being that now the input is XYZT for the time. And again, encoded as an occupancy field over time. And we can then get a very high fidelity reconstruction of that sequence. And we've done a compact optimization of this very high dimensional 3D or 4D data into the MLP weight structures here. Right. So here we see that, in fact, now we can just interpret the MLP weights as a vector of weights and biases. In practice, for our experiments, we have about 30,000 parameters here in these weights. And we can just consider this as a compressive data structure for both 3D and 4D sequences here. And what we end up operating with now are just vectors of MLP parameters. So that's the representation on which we want to learn the generative model, is directly on the weights of the MLPs. So you can see, because we do the optimization first, in order to fit to all of the train instances here in 3D shapes, 4D shapes, we can actually get pretty high fidelity reconstructions. These are just the optimized set of neural fields that we're working with as the train data, and decoded, of course, and visualized with marching cubes. You get an extremely high fidelity in terms of the level of detail, because we're optimizing on a per instance basis. And then we end up with a compact representation in terms of the MLP weights. So then we can go ahead and apply a weights-based diffusion. So we first fit to every single train instance an MLP, and then we are basically going through that process of overfitting and extracting out the weights for all of the shapes here. And then we can run a diffusion model in order to learn across the space of MLP weights. So I think this is kind of interesting that this actually works because it's not necessarily super intuitive, as in we don't have a good mental model of exactly what is encoded in every individual MLP weight. And we are trying to go to the extreme of leveraging the fidelity of the overfitting process. So we don't necessarily know exactly correlations between the nth parameter of one MLP versus another MLP, but we can try to model this denoising process directly on the MLP weights and biases with a transformer to predict this noising process here. And that allows us to sample new weights for MLPs that can, of course, then just be, unflattened and decoded with marching cubes in order to get out the actual 3D or 4D visualizations. So this is a dimension-agnostic kind of approach. We can treat 3D and 4D data pretty much exactly the same in terms of this overfitting process and interpretation as MLP weight vectors. We do train the diffusion process on them separately. We haven't tried them together, but it's the same general framework and the same number of parameters for both scenarios. So just to give a bit of a sense of what this weight space looks like, at the top, you start with random Gaussian noise on the MLP weights, and eventually we denoise out to something that corresponds to, in fact, a valid 3D shape. So just to see that one more time in terms of the correspondence between the weight space and the actual 3D structure. So when we sample from the model now, we can actually produce new 3D shapes. So here you can see for airplanes, in comparison to a couple of state-of-the-art point-based diffusion models, and also just a naive voxel kind of baseline, which is, of course, limited in resolution due to the dense voxel grid nature. But here, like the compact nature of the MLP means we get these nice kind of sharp details at the edge, at the nose or the wings of the planes, because we're actually operating in a very compressed space that contains all of this high quality detail. And here, the same for chairs in comparison to the state-of-the-art baselines and the default voxel baseline. And finally, for cars, again, because we can leverage this kind of compact data structure of the neural fields, we can get a nice distinction between things like the wheels of the car and the body of the car in the generated shapes. And so this applies also directly for 4D sequence data. So this is now, we were not aware of any state-of-the-art baseline that performs this task. So we have a voxel-based baseline here. And you can see, of course, because we have the neural field representation, we can actually capture a much higher fidelity in terms of the resolution of the deforming shape sequences here. So we also, I wanted to mention, this is kind of nice that it's actually making sense of a bunch of individual compressed MLP interpretations of 3D shapes, of 4D shape sequences. So it's really about seeing these neural fields as a sort of optimization data structure and what we can do with them in terms of interpreting very high dimensional data. But it's worth noting, of course, what's the quality of our ability to actually generate new shapes versus just recall train shapes. And so these are a visualization of the neighbors in the train set. And what we do here, in a sense, is probably not fully imagining something completely new, but rather being able to combine some interesting aspects of other shapes. Here, for instance, the bottom of the chair is similar, but not quite the same, versus the top of the chair here, as well as in the other cases. I think mostly what we're looking at is an ability to do a slightly smarter interpolation between different kind of parts in these shapes. So I think I wanted to discuss this kind of paradigm and see what we can potentially do here, actually leveraging a different kind of outlook on neural fields and their optimization as potential new data structures for generative tasks. But we've pretty much been stuck at the level of shapes here. And I wanted to also discuss a little bit what the outlook would be for scenes, because I think a lot of the really nice generative models we've seen are actually operating at the level of individual objects. So my take here, and potentially might be wrong at some point, given how much of the massive quantities of data that we're seeing in other areas, is that we actually are still missing high fidelity data for 3D scenes. What we have at the moment for real world scenes, for instance, is mostly at the level of something like ScanNet, where the geometry has very clear kind of artifacts in terms of the way that it was captured. And so using this as some kind of signal for how we generate 3D data means that we're fundamentally limited to that kind of quality. And so what we're looking at is how can we actually capture very high fidelity examples of 3D scenes, in this case with ScanNet++. So you see here in terms of the quality of both the geometry and hence also the semantic annotations, because now we actually have the ability to realize the geometry of small objects here, for instance, in comparison to something that you saw of the same kind of scene in this scenario here, not only for geometry, of course, because if we talk about, modeling 3D, it's not just geometry, semantics, it's also about color and appearance. So we're looking at capturing high quality color for the sake of modeling appearance as well as modeling radiance fields. And we're looking at not just high end in terms of the geometry, but also how can we potentially connect this to common user inputs, like for instance, with an iPhone captured data. So we're tackling that by actually going around and trying to capture all of these modalities. So we've got a Faro sensor that's capturing laser scans at about 1 millimeter resolution in terms of the geometry. As well as a DSLR that's capturing 33 megapixel images for effectively neural radiance field reconstructions. And then finally, the iPhone is representative of the commodity sensor kind of input of the same environment. So I think there's a lot of opportunities here to learn about what high quality 3D data looks like and how we can bridge this to other sources of information. So I think, we haven't completely forgot about semantics in the quest for generative modeling. And in fact, when we model this kind of high fidelity 3D data, we actually can resolve a lot of these very small, interesting kind of objects here that are in the scene that are otherwise actually very difficult to recognize when being interpreted at lower quality kind of resolutions. So this is an ongoing effort of ours. We're looking at capturing a large enough set of scenes to start to learn general priors. So that's currently at 400 and counting. In terms of the RGB frames for DSLR, we have about 200,000, 3 million for iPhone frames, and a large number of class labels for all of the objects and instances. So what we're really looking at is trying to give an opportunity for new general priors on novel view synthesis and semantic understanding. So if we look at like novel view synthesis and NeRFs, they've produced a really impressive quality recently, but we don't have necessarily a unified benchmark nor a clear way to learn any kind of general priors on this kind of data. So we're capturing both the high-end data, the low-end data, and we want to be able to also tie this to semantic priors. So we've got annotations for semantic segmentation as well as instance segmentation to try to give all of you the opportunity to develop the next generation of generative models that actually ties together all of these concepts of high quality geometry, semantics, and also color and appearance. So just to give a bit of a sense of some of the leading novel view synthesis methods on the DSLR imagery, this is captured in a way that is intended to get as much coverage of the scenes as we can, in order to be able to understand the view and appearance of these scenes. So here you see the difference between the iPhone novel view synthesis and DSLR novel view synthesis, where iPhone has been captured with the intent to represent the more common user in this case. And we see there's artifacts due to that being motion blur, to there being auto white balance and auto exposure and so on in the capture. And I think that means that there's something to be done in terms of how to combine together the high quality signal to something that comes from a more average user kind of capture. So with that, I think we're looking at the next generation for generative models, really for computer vision, bringing together geometry, semantics, and appearance modeling. And so I hope that that will allow everybody here in the audience to be able to develop their new ideas for how to really model 3D now that we actually have some samples of high-end 3D data. So with that, I'd like to thank you for your attention. Thanks to my students and collaborators for all of their hard work on these projects. I'm happy to take some questions.
Thanks, Angela. So we have a mic for questions. Just raise your hands if you have any questions. I have a small question. I think Vincent had in his scene representation paper also this kind of hyper network that was conditioning the nerve. Did you compare to this baseline?
Right, so I think there were a couple of works, including Vincent's, that tried to do a bit of meta learning for MLPs. And so those are also very interesting kind of approach to figure out how can you learn the meta network. We don't have a direct visual comparison to these guys. We took the current state of the art in terms of the point diffusion. I think it would be pretty interesting still. I think it's a bit different in the sense that we actually still train on a set of optimized shapes and try to navigate through that space that's already been fixed. And so what's kind of cool to me is this is actually doing something even reasonable in the first place.
Okay. Got it, thanks. More questions? No questions so far? When is the ScanNet++ dataset ready for us?
So probably in about 1 to 2 months. We're aiming for a first release at 500 scenes. You saw we're currently around 400. And so then we'll try to make that initial release and continue the data collection effort. So if any of you guys have some spaces to donate, let me know.
Okay, thanks. Then let's stop here and give Phil the chance to. Thanks, Angela.